And so now, as a general picture, what we understand here is that we have a linear function in two variables. Instead of taking all input pairs of values from the x and y plane, we're only going to take input values inside of the graph's region, satisfying these three inequalities together. And now, formally speaking, any of these three inequalities is being referred to as a constraint. And the entire region, the graphical region, being the solution of these three inequalities here, or being the solution of this system of inequalities, is called the feasible region. And so we're only going to take input values x and y that's being inside of this feasible region to work with our function. But so the real good application of having our function being limited to a feasible region like this, now I'm going to bring up a problem that says, so how about in our problem right here, in our current function, z as a function of two variables equals the x variable plus 5 times the y variable, and subject or limited to these constraints, then the real big application here is we would like to find, or here's the term right here, we would like to maximize z, maximize our function. So what it means here to maximize z is that we would like to find, first, we would like to find the largest value of z. The largest value of z, because you can see that z is a dependent variable now, and its value comes out depending on which pair of values for x and y, depending on different pairs of outputs x and y that we're giving it. And so in that way, what can be the largest, or what value of z can be the largest value of z? And further, we also want to, so maximize is one term, it actually means two things. We want to find the largest value of z and which pair x and y gives, it could be more than one pair. So which pair x and y gives the largest value of z. Sometimes you can understand, or many times you can also understand that this second statement of mine is that which pair of x and y makes the value of z largest. And so now clearly understanding our goal that with a given function, so here I'm using this function as my example, but we can draw out a generality that from any given linear function in two variables, subject to a system of inequalities being its constraints, then maximizing the function means two things. First, the most important thing is to find the largest value of z's, and further we find which pair or pairs of x and y that gives the largest value of z. And so allow me again to bring in the picture, the graph of the feasible region. So this is our feasible region of the function we're currently working with, or basically on any function. If we use a feasible region that came out from x plus y less than or equal 25 and x greater than or equal 10 and minus x plus 2y greater than or equal to 0, then we are going to produce this feasible region. And this feasible region has three corner points right here. There's one of them at 10, 5, another one at 50 over 3 and 25 over 3, and the other one is at 10, 15. And so to find the maximum or the largest value of z, simple work. All we do now is we're going to go ahead and substitute there is a theorem that guarantees that in order to do the work that we're doing, finding the maximum or finding the largest value of z, all we have to do is to search within our visible region and only need to search among the corner points right here. So, in searching, what I mean is, I'm going to start out with the pair 10 and 5. With this pair of value in my function being x plus 5y, I'm not able to show the function again, but our function is x plus 5y. So that means our z value correspondingly comes out to be 10 for x plus 5 times 5 for y. So our output is 35 here. Okay, and so this is the output, or this is our z value at that corner point being 10 for x and 5 for y. But we also need to do the same calculation when we're at the other corner point. So when x equals 10 and y equals 15, at this corner point, our value for z is going to change to a different value, and let's calculate it. So here we're looking at 10 for x plus 5 times 15 for y. And so our z value here comes out being 85. So we have another value of z, another output value for z at the corner points 10, 15 for x and y. And then our third corner point here, and which is also our last corner point of this visible region, then the last corner point happens at 50 over 3 for x and 25 over 3 for y. And so our final z value as a calculation, it comes out, well, let's lay down the calculation first. 50 over 3 plus 5 times 25 over 3. And so now that comes out being 175 over 3. So now back to our goal in the beginning, that we want to maximize our function z right here as a function of two variables, as a linear function in two variables. And maximizing z means we're going to find the largest value of z, but only need to be found within this visible region. So remind from the graphical work that we have seen. Remind from the graph that we have seen, and we have already done some calculation that at the corner point x equals 10 and y equals 5, then we come out with z equals 35. So now we're just simply going to make a list right here. When x equals 10 and y equals 15, we come up with a z value being 85. And so you can already see that the z value rises higher when our corner point change from 10, 5 to 10, 15. And the third candidate we're looking at, and I'm starting to use that term candidates right here. So 50 over 3 and 25 over 3 as a pair of value for x and y gives me a value z equals, calculation shows 175 over 3. And so according to the visible regions, that gives us these only 3 corner points. Then this corner point here is the one that happens to give us the highest, the largest value of z right here. And so maximizing z, we have found our solution. So here's our concluded solution. We can say that maximum value of z, allow me to skip the word value. So maximum value of z equals, what's the highest value here? 85 equals 85, and we reach that highest z equals 85 at the input pair x comma y equals 10 comma 15. And that's how we're doing our work to maximize a given linear function in two variables subject to a set of given constraints right here. And the same function given here, z equals x plus 5y, and again this is a linear function of in two variables, and subject to a few constraints here: x plus y less than or equal to 25, x greater than or equals 10, and minus x plus 2y greater than or equal to 0. So these constraints together is making up a what's so-called a feasible region. And so this function now, once we only look restricting our input values to within this feasible region, we can also minimize z. And so minimizing z means, most importantly, find the lowest or smallest value of z. And further, we want to find which pair of x and y give the largest, smallest value of z. We have already seen the feasible regions as a graph region of this system of inequalities, and the feasible regions from this system of inequalities come out with three corner points. One of them was 10 for x, 5 for y, and it came out with a calculation value for z equals 35. And we have seen all of these calculations in the earlier part of the video. Another corner point was at 10 comma 15 when z, and coming out with z equals 85 as output value. And the third corner point in our feasible region is 50 over 3 comma 25 over 3, and calculation shows that the z comes out to be 175.3, and in decimal, making it a little easier to compare, then 175 over 3 is about 58.33 repeats. And so now our search now is to find among these corner points right here, which one of our values of z is the lowest this time. And so now obviously having the complete list here, then you can see that we reach our lowest value of z when z equals 35. And it happens, we reach our lowest z value being 35 at the pair of value x equals 10 and y equals 5. And so now once we have worked and finished with our feasible regions previously and found all the corner points, the work to minimize z is now just simply concluded as we're going to have minimum value. Allow me to just use a shorthand writing min, the minimum value of z is indeed equals to 35. That's the lowest among these three output values, and it happens at x comma y as the pair of value b equals 50 over 3 and comma 25 over 3. And that is our solution to this question.